Thank you all for being here. I appreciate you taking the Thursday morning, spending it with me. I'll do my very best to make it worth it for you. I'll give a monologue. I'll gladly tell you stories, but at the same time, I am very willing, if you have a question, just raise your hand and I'll answer it. It's a small enough group that we can just be friends rather than speaker speaking. So let me start by emphasizing a few things. I will tell you some technologies. I'll tell you about things that I figure, since this is a technology licensing office that's organizing this IP event, really it'd be beneficial for you to see patents, ideas grow into companies. So I'll mention a number of these companies that Deirdre mentioned. But my goal is really to also put together kind of a story of why do we invent and what does it take to actually translate a high-tech idea into something that could be much more impactful than simply an academic discovery. And hence, it's good to start with one of the original moments of great academic ideas that Archimedes had, right? As he proclaimed, "Eureka, eureka." You know, his whole idea of recognizing something new that the world has not quite fathomed in the same concrete way before was a great scientific breakthrough. And many of us, when we stand on a whiteboard and are talking to a buddy and we look at their diagrams and we're like, whoa, wait a second. That stuff that you just drew, if I combine with my stuff, can actually lead to an entirely new way of thinking about what technology should be. That's a patent right there, that eureka moment. And that's about 10 years away from being useful. That's the part that we often don't truly understand. Inventions do happen in a moment. And quite often, once we publish the paper, people are quite happy with it and say, great, when do I buy your solar cells since you just published the first version of it? And the answer is about 10 years from now. Now, why does it take that long? Well, it just does. And it is good to think about why does it take to actually scale a new idea? Why does it take about a decade to do so? So I looked at some examples from history to kind of give us a way to start through it. A zipper, a good invention, a fantastic way to replace a button. Indeed, one would say it should have taken like a wildfire, like, the moment people invented a zipper, you should have had it everywhere. And it took, roughly speaking, about 12 years. If you count it from the first useful patent, there was another one before, it wasn't quite as good. So why is it? What was missing for people to have zippers everywhere? And first time you would find them actually used were on boots, because boots were really hard to lace, and this was one way to avoid lacing of the boots. But one thing that was missing was there were no machines to actually take small mechanical parts and put them next to other small mechanical parts to make the zipper. So for all the awesomeness of an idea, without the ability to actually scale the idea through the machinery, through the foundry that is missing, you need to invent the foundry as well. If you were a watchmaker at the time, yes, you were putting small mechanical parts together, but not at an affordable cost that everyone can go ahead and have as a zipper on their clothing. And of course, you say this is like 100 years ago. Does it really matter? Well, let's take a look. 50 years ago, 60 years ago. Another technology called the Velcro, very powerful technology, amazingly well advertised by astronauts. And that advertising blitz was quite useful in propelling the technology beyond simple invention. Invented by a researcher observing burrs sticking to the fur of their dog and recognizing, it's that hook of the burr that kind of catches onto the hook of the fur and consequently generates a really good fastening action. It took 13 years to commercialize this technology, making them reach 1 million people. And yes, I said the Apollo mission was very helpful in the process, but really what was missing is plastics were a brand new idea in the middle of the 20th century. Uses of plastics and extrusion of plastics and forming of the fibers was an impossibly new idea that without developing the foundry for it, you won't find your way of actually scaling the idea. So you look at those two ideas, and again, you can say, a little while ago, maybe something newer would be useful. All right, fine. Strained silicon technology, invented in 1990s by Judy Hoyt, who unfortunately passed away just last year. Judy, together with Gene Fitzgerald, thought of ways, Gene is also here at MIT as professor of material science, thought of a way of generating a higher mobility silicon by introducing a little bit of germanium as a dopant that stretches the bonds of silicon, separates the heavy hole from the light hole. Light hole becomes the dominant charge carrier method, and consequently everything becomes faster. Amazing way to speed up your transistors. And every electronics companies of the 1990s should adapt it. How long did it take? About 13 years. And it was desperation, not wanting to change the technology. It was desperation in competition between different companies that led one of them to say, fine, let's try this crazy scientific idea that should obviously work because scientists have proven it. But I don't want to risk my foundry to take these, yeah, they're like silicon wafers, but they have a little bit of germanium. And yeah, I know germanium is not poisonous to anything, but you know, it's germanium, it's different. I don't want to change. I don't have a foundry for it. Well, yes, you do. You just need to go and take the gutsy move to actually adapt it. And again, you can tell me this is 1990s, you know, give me something newer. Like, fine. How about this one? High-K dielectrics. High-K dielectric is a dielectric layer right on top of your silicon channel, and it's used to turn on and off your silicon transistor. The higher the dielectric constant of your dielectric, the lower voltage you can get away with to turn on and off your transistor. Energy of a transistor spent to turning it on and off goes as voltage squared. If I can halve the voltage, I'm quadrupling the reduction in energy of utilizing that transistor. So this is a huge deal. Everyone should just jump on it. And of course, over a decade later, everyone did. But it took a decade for this to be adapted, because again, hafnium oxide. Well, I don't know. Will hafnium mess everything else that I have in my foundry? You have to test it. You have to prove it. You have to find a way to convince the next guys over. I'm giving you this only to say that for as awesome as many of our inventions are, as we stand on that whiteboard, and as awesome as our academic papers are that we publish, very few will be adapted. And if they are adapted, they'll be adapted a decade from the moment you invent it. Adapt that as a reality of how the things are being put together. Now, that's good to know, because if you recognize that the journey will take about a decade, and the journey needs to be continually supported, another good number to put forward is that it's going to take about $100 million or more dollars to go ahead and actually get it executed. In a history of recent humanity, we have never made a new technology for less than $100 million. And if you can ask someone to give you $100 million to make this technology, you better have a proof to them that you're going to make them $1 billion back. It looks like techno-economics is the key for us as scientists and engineers to be useful in the world, which is one of those other things that we often don't spend enough time, I think, in our engineering and science classes in recognizing, at least if we are aiming to make a technology that's meant to be transformative. So the goal of the following number of things I'm about to show you is to show you some journeys that indeed worked out, and some that are still nascent, and who knows if they're going to work out. About 20% of the greatest of ideas will succeed. Not because they are bad ideas. It's just because something changed about the universe during the journey of 10 years that the initial assumptions needed to be modified on the fly. Most of the successful startup companies in year 3 or year 5 have a pivot. They rethink who they are and what they do. And that pivot is what saves them or folds them because they haven't made the right pivot. That is because everything does change on you, and consequently about 20% of the really good ideas are the ones that actually become successful enough. Bear that in mind as you're thinking about the next great journey to take. So my goal is to summarize this in the following way, just a couple of things. The foundry is really useful. Unless you have the foundry, you need to go ahead and spend about 10 years in converting that basic idea into impact. And I will focus on what I refer to as ubiquitous active surfaces, ability to have these unusual nanoscale materials that we now can control, thanks to the tool sets of today, to indeed rethink what the next set of active technologies could be. I'm going to show you a few of them, and I'll give you my modified thinkings of why did we think that these would be the good ways to go about doing them. The work I'm showing you is done by dozens and dozens of amazing people who were in my lab. I am tremendously lucky to have seen generation after generation of extreme talent go through my MIT lab and actually take the next set of journeys. So these are not my achievements, these are my co-achievements with my colleagues who have done an amazing amount of work to make them real. You're looking at one of the future technologies. I'm not sure it ever will become a technology, but this is an invisible display, a display that looks like nothing. It looks like a piece of glass until you shine some UV light on it. And when you do, it's going to start glowing back. All it is, my friends from chemistry would know, are colloidal quantum dots inkjet printed to make a thin film. And then if you make them so thin that you optically imperceive it, don't see it, and consequently, only when you optically illuminate it with the right color of light, you can get them to glow back. A different way of thinking of what the display can be, but it's a sub-micron thickness display that could be ubiquitously deployed as an active surface, if that's what you wish. I won't spend much more time on it, because it's a simple idea, simple technology. And this also seemed like a simple technology. A pickle, electrically excited. If you apply 100 volts on it, it glows. Amazing glow of sodium atoms inside it. You can slice the pickle very, very thin and lay it in a pixelated format, and you can make yourself a $40 billion industry called organic LEDs. Now, I'm not using atoms here, I'm using molecules, I'm electrically exciting them. And it's a journey, right, to go ahead and develop something like this, because there is no foundry. It's a novel kind of semiconductor. And indeed, the physics of it was not completely understood. So the journey actually took about 25 years from the moment of I can make an efficient OLED to million people using Samsung Galaxy phones to go ahead and demonstrate the value of this technology. The challenge of this technology, though, was that it's utilizing materials never before used. It's utilizing them in a format that has never been previously done. As a matter of fact, the materials it's using, the carbon-based materials, have been universally maligned as unstable, as easily oxidized, as hard to process, as impure. Gosh, why would you ever, as electronical aficionado or electrical engineer or scientist who wants to make this thing really work well, why would you ever even look towards these materials as a way to go forward? Silicon is your answer. Well, it doesn't glow. Okay, let's find something else that glows, but it has to be silicon, right? Like, because that's we understand. The challenge of OLEDs actually tells a tremendous amount of insight. When you look at that Samsung flexible OLED screen, there is something truly unique about it, which is that it's a screen that bends. Do you ever need it? Actually, you don't. No, you never read your newspaper bent. You always hold it as flat as you can, right? So if you ever read newspapers anymore. But the reason why I went with a newspaper is to show you that here's an object I'm hoping can be flat for me to read it. So what the heck could possibly be the value of a flexible display? That's ridiculous. And it's not the flexibility that's valuable. It's the thinness of it that's valuable. As a matter of fact, most of us don't remember, but some might, when the first time liquid crystal displays were introduced into the world. There were these huge boxes called CRTs, and now we're going to have these flattish, like 1 inch or 2 inches thick screens called liquid crystal displays. They looked horrible. Like you look at the screen, you're like, I can see it's a picture, but it's not really very colorful. It kind of lags, like there is a blur of the image, but man, is it nice because it's thin. And you're like, why does that matter? That's not the picture. That's not the screen. That's not the value of the screen, except it is. That's what consumer really wants. They want less space in their room occupied by a box that is a TV. They want the ability to add it to an electronic box and make it into a laptop. They want it so thin that it's imperceptible, if at all possible. And that's the wave that OLEDs took, except OLEDs returned the quality of the color, made them more energy efficient, and also gave them that extreme thinness. But it required an entirely new material set. And so here is the awesomeness of OLEDs, or quantum dot LEDs, that I'll mention in a moment, which is the power consumption per inch squared dramatically is reduced compared to the standards. Else liquid crystal displays, plasmas, rear projection TVs, these are ancient beasts of the times past now, but were the standard ways to display technology 10, 15 years ago. OLEDs had these advantages of high contrast, super thin, ultra fast, pure color, curvable, with the one significant deficit. They require large area nanofabrication technology. So present this to any rational technologist, and they'll say, well, you know, it'd be really nice to make OLED displays in a large pixelated format, but since I know the industry, I'll tell you this. Apparently, every one of those 4 million pixels needs to work. Well, that sounds like an obvious statement to you and I, because we expect TVs to have every pixel that works, but that is not the way electronics works. Inside your chip, like M2, M1, that is running your laptop in there, 10% of transistors do not work where you expect them to work. 10%, sometimes 20. You know, when you're like going to a store and you're buying a 3 gigahertz machine or a 2 gigahertz or a 1 gigahertz machine, no one ever intended to make the 1 gigahertz machine. That's the machine with a chip that has many bad transistors. And they slow down the chip so that you don't see how badly it will perform at high speeds. That's the way to use the deficit of making, of the ability to actually make absolutely perfect every pixel working. And I'm going to now tell you, now make me electronics technology that has never been made at a yield that I need for the display. Oh, and by the way, your eye can pick 2% difference in brightness between neighboring pixels. So every one of these needs to work to within 2% accuracy of each other. Again, never done before. At the yields never done before, with material that has never been used before, at material thicknesses that are way thinner than a critical dimension of any previously made electronics technology. Oh, and by the way, your chip is not 1 by 1 inch in size, but it's going to be 2 by 2 meters in size. That's ridiculous to even attempt making a machine for. But if you're an MIT student, the answer back to me is, well, is it impossible? Well, no, it's not impossible. But it's highly unlikely that you're going to get all of those milestones met. And consequently, in a rational world, I'd say don't bother. Except you look at the enthusiasm of students and they're like, well, you know, is it impossible? You know, we can go and calculate, is it ever possible for us to do this? And calculations tell us, yeah, it's doable. There is nothing really, really stopping us except it's never been done. So they make things like this. They launched a company called Cativa. Cativa was launched in 2008, and by 2016, December 2016, their tools were in factories in Asia. This is a small version of their tool. This is a printer. It's using a 2 by 2 meter piece of glass, and it has this glass sliding back and forth. That print head has 1,000 nozzles. They are covering the entire area with active polymer or passive polymer, depending on what's needed. It's primarily used these days for encapsulation, extremely accurate encapsulation tool sets. It can deposit quantum dots. It can deposit molecules. It can be used, as it's being used right now as well, for OLED manufacturing. And by the way, that whole area of a 2 by 2 meter piece of glass, you have 75 seconds to cover it with a layer of material. With a 25 micron positioning accuracy, few nanometer thickness accuracy, 5 micron definition between lines. Every one of the pixels needs to work. Sounds impossible, but if you have enough cleverness in the way you've designed this, understanding of materials, and then also software that continually monitors what you've done and adjusts on the fly for the errors that you make, you can make an extremely powerful machine. Cativa's tools in just the first year of operation encapsulated 100 million cell phone displays. And the tool I'm showing you there is one of these early ones, like roughly the Whitney one up there. Actually, I'm sorry. Yeah, between Shasta and Whitney is the one that I just showed you. They use different peaks in California and mountains to name all their machines. And as the time went on, they done better and better. Today, they are the leading supplier of inkjet equipment to OLED display industry. If others have tried copying their tool sets, they require 10,000 different parts providers that need to work just right in the just right way. And others who have tried copying their machines have not succeeded because of everything that takes to actually make it work. But the company now employs several hundred people that are over in Newark, California, just north of San Jose, that is developing these for whoever needs them, and many people do need them. They are looking at other ways of branching out in new types of technologies. It's a story that I would never tell you ever to try to attempt to reproduce, right? Because it's one of these, like, it is so hard to make a foundry for new materials, but they've done it. And although I've told you I would never tell you to try to reproduce it, here is another story of reproducing that very same idea, but now in a different material space called colloidal quantum dots. Colloidal quantum dots themselves are beautiful to electrical engineers like myself. I love the fact that you can choose the size of the dot and not change the chemistry of it and still get a different color. I love the fact that I don't have to know too much chemistry. As long as I can stick with one chemistry, I can get to places to actually make things really work for me. It also is tremendously satisfying to have really good colleagues. And since I joined MIT, I worked extremely closely with Munji Balwendi. You might have heard of him. Recently, he won the Nobel Prize in Chemistry for colloidal quantum dot synthesis. The beauty of the work is that the journey did take about 30 years to go from the basic discovery of glowing dots to the scale-up of those glowing dots in a practical technology. And let me show you some of those practical technologies. Back in 2009, they made the very first really good-looking light bulbs. Now, they were upped by one other company before them who made Christmas lights that put a little quantum dot on top of a LED to make different monochromatic Christmas lights. But, you know, that's cool. But what was cooler was to be able to look at the incandescent light bulb, realize that a cool white LED that was made at the time, illuminating a bowl of fruit, would make your bananas not look so appetizing. However, if you take a cool white LED and add to it a thin layer of so-called QD optic, you can generate the perfect glow of an incandescent light bulb. Brian here might know a little detail or two about it because he was in the middle of that story. But 60 lumens per watt is about 5 times more energy efficient what an incandescent light bulb can do, and yet, from perspective of a user, looks exactly the same color-wise. This is a way of rethinking what a light for you does. 20% of the world's electricity is used on lighting. If I can reduce that by taking LED lights and maintaining the quality of the light, people will be much more likely to adopt it. And I can save a whole bunch of energy otherwise that would not be, otherwise saved. The opportunity is very large, but you need to make a business out of it. And for as awesome as Q Division's vision was, as a matter of fact, this was the very first pivot of Q Division, the little startup that commercialized this technology starting in 2005. Their very first picture of who they are is a company that's going to replace OLEDs using the quantum dots as the light source in an OLED. The thing we missed is that there are no foundries for OLEDs or QLEDs back in 2005 when we started this. Cativa did not make their first tools yet. Cativa didn't even exist. They incorporated 3 years later. And Cativa's demonstration of a quantum dot printing, that just happened over the last few years. So the ability to actually make a pixelated display out of quantum dots, yes, I can do it, but I needed the tools that Cativa has now in order to use the chemistry and materials that Q Division developed at the time. Timing is everything, and having that full vision was really important. So Q Division recognized that this is indeed not going to work quite well for electrically excited quantum dots and said, well, what if we do optically excited quantum dots? We can use gallium nitride LEDs that are electrically excited and absorb the blue light from the gallium nitride and give you the light of the quantum dots optically excited. It works extremely well. The dots last forever. There is nothing that kills them, it appears that way. Electrically excited dots don't last forever. I'll tell you at some other point if you really want to know why, but optically ones, amazing. Great mix. Fantastic business. Economist writes a story about you. Boy, are you flying high. Light bulbs at the time were costing about $20 to $40 a light bulb. That's great. All I want from a light bulb maker is to give me 5% of the value of the light bulb, right? You get $2, so give me 10 cents and I'm fine, right? $20, give me $1 and I'm fine. That's all I want. But the problem is this second story, which is that the light bulbs went from $20, $40 down to $2. And what used to be $1 per optic dropped down to 10 cents or 5 cents an optic. I can't make a business out of it. I mean, waking up in the morning and picking up a box of optic, that costs 5 cents, right? If not much more. I can't make the business out of it. I need more expensive light bulbs to make. So the brilliant scientists and engineers and business people at Q Division said, well, every TV, like this one, or a screen, has a light bulb behind it. Those are more expensive than a couple of bucks a piece, because you're selling the screen for $100, $1,000, right? I mean, I can ask you for like $20 to pay for my good-looking light bulb, especially if I can replace the light bulb and make your TV look better. And that's what they've done. They replaced every white light bulb behind an LCD screen with a light bulb that had a blue emission from gallium nitride, very sharp red emission and green emission from the quantum dots. Now you had a perfectly saturated blue, green, and red shining through your liquid crystal display filters, and as a result, the colors you were seeing out were also pure and saturated colors. Take my light bulb, put it in your today's LCD screen, and you'll make your LCD screen look way better. Well, that's an edge that many of the display makers would like to have over their competitors. And in 2013, Sony introduced the so-called triluminous quantum dot enhanced LCDs, showed it in January 2013 at the Consumer Electronics Show. They won the best TV of the show. The world was going to, from now on, know that what the world needs is a quantum dot enhanced TVs. And Q Division will be a successful company that will forevermore be known as the one who introduced and pioneered and grew the quantum dot industry. Now, that's a great story to tell, right? It didn't quite work out that way. It didn't quite work out that way because there are business pushes and pulls. The moment you start being successful, you're in the target of everyone else. And all the other guys would love to buy you, but not for very much money if they can. Next 3 years that followed were not a Cinderella story of Q Division. It was actually quite a bit of a struggle between different makers who wanted this and that, between other quantum dot companies who felt that Q Division has infringed their patents, despite the fact they didn't, but sued them here and there, because they now might have money coming from Sony, so maybe they can pay. The best thing to do in those cases is either fold or look for the next best opportunity to give to the world. And in this case, it would be to ask Samsung, or Samsung asking you, do you want to be bought? And you might as well. You're struggling in every other way to survive. QLED technology that Samsung introduced is originated from the Q Division's vision of what they've done. And QLED technology today, after acquisition by Samsung, is about $4.5 billion industry. That's good and is growing. Every TV that you go in the Best Buy and look for, if you look at the best looking TVs, they're either QLEDs or OLEDs. They are the ones that give you most lifelike images. And quantum dots are truly remarkable in the way they're operating right now. The latest version from Samsung actually combines an OLED with a QLED. A little bit of a crazy technical idea. They use blue OLEDs and put quantum dots on top to make them beautiful colors. We can discuss, is that good or bad idea? But from perspective of beauty, it's an incredibly powerfully looking TV, enabled by the vision of what Q Division did and what the MIT labs initiated, and what those crazy students that said, we're going to scale up the making of the quantum dots, never done previously at the scale. Well, we can do it. We can do it. So I am always in awe of that drive that students have. And I was wondering, why is that? How do you actually launch new ideas that truly, truly make a difference? I realized I was talking to a CTO of a notable European company who was, the day before we were talking, he took me to dinner, and I had this nice dining area, in one of these European little villages, and picket fences, and little flowers, beer garden, cobblestone. Oh my gosh, was it gorgeous and beautiful, and nice sunshine coming through. The next day, he tells me, I want to start an innovation center, down the hall here. It's going to be separate from our main building, and woods over there. And how do I do it, Vladimir? I'm like, I don't think you can. He's like, well, what do you mean I can't? I'm like, I really don't think you can. I think one of the main ingredients for launching a new idea is to have the motivated inventors who believe that this is the best thing since sliced bread. The one benefit MIT has is that every year we fire a quarter of our best people by giving them degrees and kicking them out and saying, you have had a fine and steady life up to this point, but at the moment of graduation, everything changes. There's a cliff. You're about to go into the abyss, because who knows what the future is. It's undefined. You need to shape it. And it's that desperation for what is coming next that makes them, a third of them at least, jump into, I'll start a startup. I can build the world. I mean, after all, we spend time telling you your job is to build the world of tomorrow, and you're not going to do it by joining an existing company. You're going to do it by building a new company, by building a new idea. And combined with the fact that you're desperate for a job, gosh, that's fine. Let me do it. Versus a little quaint European village with workers who already are working in your company, get paid reasonably well to have a picket fence and flower garden. Here's the thing. Stop that job so you can join the Innovation Center. There's a couple of things you should know. You might have to work 7 days a week, 10 to 16 hours a day. You won't see your family very much. You might get paid a little bit below your present salary. And 10 years from now, there's a 20% chance you'll be successful. Come join the Innovation Center. That's what you're saying. That's not an easy thing to jump into. Unless you've been an entrepreneur before and you have yourself some confidence behind you and maybe some financial cushion to actually go ahead and say, this is fine, I'll try out another time. But for a young person who is just coming out of MIT, doesn't have necessarily all the responsibilities maybe of raising a family or such, that is a more obvious job to take. And so the best innovators are those young entrepreneurs, the ones that are indeed seeing their work, that they spend 5 years working in their laboratory and as the best thing since sliced bread. And consequently, they are the ones committed and would work for pennies and sleep on a sofa and eat, cheese and bread sandwiches for a week or two in order to make sure that that particular idea gets over the hump so they can get the next round of funding to be able to take the next step. Forming a great idea is hard. Building a great idea is harder. And I don't want to discourage anyone, because I think all of you can do it. But at the same time, you should have that sense of reality of what the journey truly looks like. And can lead to glorious moments like this as well. Mungi's Nobel Prize was a tremendous validation of everything QD Visions has done as a company. And certainly to us at MIT, extreme pride for being colleagues with Mungi and seeing that next set of great ideas. There are many more things I can say. I should stop around 11:30 or 11:15. What's my timing? 11, okay. So I'll keep on going, tell you a few more things. And then you guys can tell me to stop or ask questions as you wish. I'll show you one other idea, or a couple maybe, which are more solar oriented. So rather than emitting light, how about we absorb some light and make some electricity? After all, the world needs more renewable energy. The world needs more renewable energy, and I guess in my mind, The question is, why don't we have even more of it? And the answer is we are doing really, really well. 4 or 5% of the world's electricity is provided now by solar. If you asked me a decade ago, I'll tell you that just about 0.1% of the world's electricity is provided by solar. Solar has been increasing year after year at about 20% overall rate. I mean, if my bank account was jumping at a 20% interest rate, I'd be doing really happily, right? But that is what solar is doing, is growing at that astronomically fast rate, and yet it's not quite fast enough. We need to cover roughly the area comparable to all the roads of United States with solar cells. That's what we need for the planet to be indeed energy collecting in a renewable fashion way. That's hard to do. It's hard to do because actually solar cells is not what costs in the overall installation of the solar field. It's the installation process itself. That's what costs. If I can make installation simpler, I can make a dramatic change in how rapidly we can deploy the next set of solar cells. And so we looked at what would make solar installation simpler. And the answer very simply is weight. Get rid of the weight of the solar cell. A typical worker by law in a construction site is not meant to be picking in repetitive fashion anything heavier than 50 pounds. Otherwise, they can get hurt. So if they're not going to be lifting anything heavier than 50 pounds, my solar panel cannot be heavier than 50 pounds. That's the weight of 1 by 2 meter panels of solar cells today. And that's because they use 4 millimeter thick piece of glass and a chunk of silicon that's very thin, but very fragile. And they need a 4 millimeter thick piece of glass so that if the glass bends, well, the glass can't bend if it's that thick. And consequently, silicon wafer will not crack. If you do try going 3 millimeters, your silicon wafers are likely to crack, so it develops so-called micro cracks. So I need 4 millimeter by 2 meter squared area of glass. That's 50 pounds. If I can get rid of that piece of glass, I can make a much more valuable technology. I can't get rid of that piece of glass unless I get rid of silicon. So let me use something else. And so what we started using is organic thin films, perovskite thin films, and asking questions, is it possible to make an extremely lightweight cell? The answer is you can. You can make them extremely light. And you can make them on plastic. You lose some weight, but not too much. You can make them just floating on their own. Now they become too fragile. You can rip them very easily. What if we can just add them, those extremely lightweight cells, on top of a fabric, on top of a substrate that will not break? Fabric was our choice because you don't rip your shirts very often. And the vacancies between the threads of the shirt give you the lightweightedness. So you can make fully printed, large area, transferable photovoltaics on fabric. These are, when you finalize them, they weigh 100 grams per meter squared. So 2 meters squared would be 200 grams compared to 25 kilos for a conventional cell. So we're talking about a factor of 100 less weight per meter squared. Final structure of the thickness is about 50 microns. Your hair is 100 microns in thickness. We are thinner than a strand of human hair when we finalize this structure. Is it rippable? Actually, it's not. The fabric we're going to use is a fabric that is utilizing bulletproof vests, kind of like Kevlar. It's called Dyneema. It's a fabric that is extremely strong. When a ship got stuck on the banks of the Suez Canal, they did not use steel cables to pull it off the bank. They used Dyneema-made cables because they were lighter and stronger than steel. So let me make a fabric out of it and put on top of it our solar cell. And you're going to get yourself an extremely lightweight technology. This particular technology is driven very much by, can I give you a format for rapid deployment? But can I also give you a more economical technology? Because at the end of the day, I can give you the best solution. unless it makes you money, you're not going to spend money installing it. Not to say you're making a bad choice by not installing my expensive solar cells. You're making a right choice economically. You're not trying to save the planet, but is it your job to save the planet, right? I mean, you can say back at me. So my goal would be to both make you economical sense as well as technological sense. So we gone ahead and did a one quick weekend back in 2017. I was hanging out with my high school, one of my kids who was in high school, and I asked her, can you help me figure out the prices of all of the most sold vehicles in the United States? It sounds like a ridiculous thing, but I had an idea behind it. So I said, can you, if you give me Toyota Camry, it comes in different models, the gold-plated one and the one that's basic. The basic one is what truly costs, right? The gold-plated ones are all fluff. So give me the basic model price. And since you're looking up the price, just also give me the weight of the vehicle. And let's make a plot of, since I know how many vehicles were sold of Toyota Camry versus Honda Accord versus Ford 150 truck, let's make a plot of what's the volume of sales and what's the price per kilo of the vehicle. Every data point here shows you one vehicle. And notice it's a semi-log plot. So let's ignore these guys. Those are extremely small volume sales. The moment you get rid of the extremely small volume sales, every car in the United States that you buy costs the same per kilo. Really? I showed this to Chris Knittel, who actually kind of advises companies about how to set the price of a vehicle. And I'm like, I can help you. I was stunned by it. I mean, I was surprised by it. I'm like, does this hold off in other markets? And the answer is, I'm not an economist. What the heck do I know about economics? But I'm curious about these things, right? I'm looking around to find, is there an underlying reason why things cost the way they do? So I'm like, well, I don't have the data for the other items in the world as detailed as I have the data for the cars. But I can look, let's say, for the most sold models of washing machines on Amazon or refrigerators on Amazon. How do I know what's most sold? I don't. But I can look at like highly rated ones or ones that have like many comments. So a whole bunch of people must have bought them. So let me go ahead and show you very much non-statistically valid set of data, meaning I haven't done the same kind of, let's look at every vehicle sold. And this is what you find. 80% of the vehicle weight produced is in this chunk. On the left are the basic commodities, like foods, starting materials. Yeah, they're from like $1 to a few dollars, depending what starting material you buy. And over here on the right is the finalized items. Flat panel TVs, cars, AA batteries, bicycles, air conditioners, refrigerators. Notice that everything you buy in Walmart or Target is somewhere between $5 and $20 a kilo. I don't know why. I think it has to do with the number of synthetic steps you choose. Those of you who are chemists, we've done this study once ago. We've gone ahead and tried to figure out, if I'm trying to make the following chemical, how much should I charge for it? What's the cost of making the following chemical? And the answer was very simply, how many synthetic steps do you take? That actually was very powerful because I needed to know how much money can I spend on an active layer of a solar cell in order to meet the particular price point for solar electricity. And what that taught us is that if you go beyond 3 synthetic steps, your chemicals will cost way too much to make them economically viable in a solar cell. So give me a very simple synthetic process and I'll give you something that I can sell at a low cost to the consumers. It's kind of like saying, if I'm making a Jimmy Dean sausage, I needed to start with grain, and then I needed to feed it to a pig, and then I needed to, slaughter the pig and sell the pig. And every step, not the best example. Every step of the way, I need to invest in the next synthesis of going, or start with a tree, cut it down. After you cut it down, make it into planks. After you make it into planks, lay it into a structure, make a wall, build a house, right? Every one of the things you've ever done takes synthetic steps to get there. Give me as few as possible and you'll get myself a point. The thing that I can take out of this is the conventional silicon panels are about $5 a kilo today. If I can maintain my lightweight cells to also be $5 a kilo because of the processing steps I'm going through, and I'm giving you 100 times less weight per panel, I'm really reducing the cost of electricity by a factor of 100 if I'm at the same efficiency. I'm not at the same efficiency. My cells are half as efficient. I'm still reducing the cost of electricity 50-fold. That can make a difference. That can make a technology that truly can be transformational. That is the motivation for building the lightweight cells. And if you're extreme about, as I am now becoming, on looking at these numbers, I asked the very simple question of what would be the cost of MIT Nano per kilo. So it turns out that MIT Nano is about $14 a kilo. This is not the premium that you pay to the builders and such. This is, cost of materials to actually build it. There's a couple extra bucks for the premium of actually building it. Make it weigh less, it will cost less. That's one way to look at it. Why do cars stop at $14, $16 now per kilo? I don't know. But I'll tell you that the buying power of a typical worker in US has not changed since 1980s. And as a result, there's only so much of your salary you can spend on a vehicle. And as a result, don't give me a gold-plated doorknobs as a standard, because that's an extra synthetic step that I can't afford. So minimize it. Cars in India cost about $5 a kilo, but you would never ride them on US roads because they don't have airbags, they don't have safety belts. They're minimized. Synthetic steps were stopped before you give it to the consumer because it's acceptable to that consumer base to take it that way, not for us. If you do the same plot for Ford Mustang from 1970s through today, you'll find it always costs $16 a kilo in prorated dollars. Just saying. So the randomness of these choices that I just made you, that kind of the guidance on how to think about the next technology, displays are not about an image of the display. Display value was in the flatness of the display. The value of the solar cells is not in the efficiency of the solar cells, although mind you, give me as high efficiency as you can. I think the value of the solar cells is in the lightweightedness of the solar cells. That's what's going to bring down the cost. I might be wrong, but if you look at the solar cells installed on a Jimmy Carter's White House, they look exactly the same as the solar cells we use today. We have not changed the format for the last 50 years. Format is what's killing the cost. Format is what's making the cost so high. So let's figure out how to change the format in the process. The other thing one can imagine is making a solar cell that is invisible. And this is another startup called Ubiquitous Energy that got formed. Using molecules, you can optimize the absorption bands and you can make the absorption in the visible part of a spectrum diminish down to nearly zero, while the infrared absorption and the UV absorption still exists. So you can make a solar cell that you can look through, and the open circuit voltage of the series connection of a whole bunch of the little cells here added up to 106 volts under sun shining onto it. So you can make very high efficiency cells that are imperceptible by simply making the trick of nanomaterials giving you the optimized absorption spectrum. Ubiquitous Energy took that and made cells like this. This is a piece of glass, and if you attach electrodes to it, make sure there's a motor at the end of those, shine some infrared light, and you're going to get yourself electricity out of that piece of glass. An extremely powerful technology. that can make you rethink where you will find your energy source. Of course, if you stop the infrared light from shining on it, the electricity stops. So is it that your glasses from now on have a way to generate a few milliwatts of power so they can power your hearing aids or your Bluetooth radio? Is it that your Kindle can now have an electronic surface that recharges it in a room light in a course of 5 days, or the outside light in the course of 30 minutes? Or is it your whole skyscraper has windows that 20%, 25% of the electricity of the skyscraper is now covered by the windows? Those would be very different ways of thinking of what energy can be provided by rethinking what a solar cell looks like and labeling it not a solar cell, but an active surface that happens to advance itself through the nanostructure of the material itself. So the active surfaces, the work that Ubiquitous Energy has done to make these active surface, to make a truly transparent structure, they've done one quick analysis and estimated, well, what if in the 1980s, when the low E glass started being adopted, what if instead we adopted Ubiquitous Energy's electricity generating surface? How much gigatons of CO2 would we offset using these PVs? About 2 gigatons of CO2 would have been offset today if this is what we started doing back in the 1980s. That's a huge impact. That could be done by simply adding an extra layer on what already is a coated piece of glass. Installation doesn't cost you anything because you need a window. Making of it, minimal. You're not even using a piece of glass to make your cell. You're using someone else's glass. All you're adding is a micron of material in 3 or 4 layer stick. Very different way of thinking of what technology can be. I'm not going to mention acoustically active surfaces given the time, but I will emphasize that there is a practice of innovation and there is a science of innovation. And what's very obvious in the analyzing of innovation, it's a long journey that is dramatically hampering development of hard-tech technologies. And that is manifested by simply looking at the venture capital investment into hard-tech ideas like the ones I've just shown you. Less than 1% of the VC money, as PCAST report tells us, is invested into hard-tech ideas. And annually, about $160 billion is invested in startups by the venture capital community. Gosh, wouldn't it be nice if we could double this number? We would have twice as many technologies. And we really wouldn't take money from others, given the fact that most of it is already invested elsewhere. We might have an idea on how to do that, and that's what we are trying at MIT Nano. The goal is to make a journey, to make a hard-tech startup into a VC investable investment. We need to shrink the amount of time it takes to scale the idea from over 10 years to maybe 5 years. I told you historically we have never done it in less than 10 years. I just need to make it appear to the VC that it's only 5 years away. Not bluff them, but actually make it so that truly in 5 years they can do it. Which means the first 5 years of the development need to happen without VC funding. Well, that's very expensive. If I need to build a facility, get my microscopes, install my tools, hire a chemical safety officer, ensure that my quantum dots are proper. These are really hard things to do. But it turns out someone has already done it for you. And that is what MIT Nano can be as another element of how to launch the next set of innovation journeys, which is, people often speak about, a valley of death. And working with one of my students, Rich Swartworth, he says, well, there are really 3 valleys of death. And I started recognizing really there are 3 valleys of death. The first valley of death is valley of death of an idea. You have a fantastic idea and you need someone to just give you a little bit of money to get going. Then there's a valley of the prototype. Once you have the idea, can I make it into something I can show to the possible investors? And then finally, it's looking all good. Prototype is working. I have the way to scale it, except I need the last 85 million to actually build a factory. The first 2 valleys are only 15 million. I say only because that's relatively small on a $100 million scale. And this last one is the hefty one. Let me ask the VCs for the last one. Because this first two, that's my first 5 years. This last one, that's the next 5 years. So I need to present your idea right there at the end to the venture capitalists. And it turns out, right now, in today's model, looking around at different statistics, I'm going to wave my hand and say about 10% of good ideas get funded to become, towards becoming a prototype. Of those, maybe a quarter actually get funded to think about making a prototype into something that looks like a process. And then of those, maybe a third are actually funded to become real products. So multiply those numbers, that comes out to less than 1% of really good ideas ever get to the stage of being scaled. My goal, though, would be to figure out a way to make those first two valleys of that a little bit shallower. And access to existing shared academic facilities actually is the key to that. If I can make it so you don't have to build your facility, you can use the existing tools. You still need money. You need to pay me a little bit to maintain my tools, but you can use a $7 million microscope for $100 an hour. If you need a $7 million microscope results to make your discovery, I'm fairly cheap from perspective of doing it yourself, right? You can dramatically reduce the cost. And maybe I can shrink the first 15 million into maybe 3 or 5. That becomes an angel investment. So that you have a cousin or who happens to have made some money, and the rich uncle, or one of the angel investors that says, hey, I'll give you, I'll support you, I'll think you're real. And then you can take that next step of standing in front of a VC, showing them something that works, or failing, but failing on a cheap. The goal overall is give me more chances. Bring more of the startups to that last value of death so that, yes, only 33% of them will get funded, but 33% of a larger number of opportune startups will get funded. And maybe we can move that VC investment from 1% to 2%, maybe even 5%, and bring 5 times more technologies to the world. All right, I said plenty. I'm going to stop here. Thank you so much for your time.